Dante Certification Level 2, 2nd Edition. Clocking from a Layer 2 perspective. In this chapter, we'll go well beyond the basic settings in Dante Controller for choosing your clock leader. We'll look under the hood and see how clocking actually works. We'll differentiate between a traditional BNC clock distribution for, say, video or word clock, as opposed to a modern network synchronization setup. It's my personal belief that most technicians don't actually understand clocking very well. And then when something goes wrong, human nature kicks in, we tend to blame the thing that we understand the least. So by going through this exercise, hopefully we'll walk away with a skill and some confidence in clocking, and we can stop chasing ghosts in the system. So as we learned in Level 1, audio devices will take amplitude readings at a steady sample rate. Video devices will read frames of video at a given frames per second. In either case, the devices will have a steady rhythm of data exchange that needs to be adhered to, almost like gears locking together. So let me just start with an audio example. Here, a stage box captures a digital word, and of course it transmits that digital word to the next device while it's reading the next digital word. And the system just marches on, processing and handing off data down the chain. Now, the most common tech support problem came when people would call in saying, "I don't know what the problem is. I set everything to 48K internal. What could possibly go wrong?" Well, when you set things to internal, that means each device is following its own internal clock. And you can imagine if you and I were to synchronize watches and then come back a month later, our clocks wouldn't show the same time. There would be some drift. That's the problem here. When every device chases its internal clock, they'll all be approximately 48K, but maybe not exactly. Now, if I draw tick marks to represent their readings over time, I think we can explain how the problem occurs. If we zoom in on a section here, we can see that the clocks are staggered. Now, these are out of phase, which means they're slipped in time from each other a little bit. Now, that's okay because most digital devices will have a short buffer on their front end to absorb minor variation from device to device. But we would still consider this to be in sync because both devices are counting the same number of clock events in the given period. If I look from the bottom device to the top, I expect one event and I see one event. If I look the other way, I expect one event and I see one event. So this is all fine. Now let's turn our attention to a later period in this series. At first glance, you might think this section is okay because the clocks are lining up quite closely. However, if we look at the top stream, we expect one sample and we get two. If we look the other way, we expect one sample and we get none. And this is where we run into our problem. Because two devices are running at slightly different frequencies, this same problem will happen in the same direction over and over again, eventually causing either a buffer overrun or a buffer underrun. And of course, that's when we start getting our pops and clicks. So that's when people think, you know what, I'll just have one device follow the digital input from the other. Every time you receive a digital word or a section of a video frame, you use that as a clock pulse. Now, this technique is called time division multiplexing, or TDM, and it works fine for synchronizing two devices together, but you cannot do this for a chain of devices. Each handoff takes a bit of time for devices to read the signal from the device before it, and we call this propagation delay. Now, propagation delay is not a metric unit of measure. It will vary from device to device. But for now, let's just go with the concept. As our system gets larger, that propagation delay increases down the line. Even worse, each device will have a plus or minus variance in it. So as we go down the line, each device experiences its own variance plus the variance of all the devices before it. So again, this is fine for chaining two devices together, but it's not a very good method for synchronizing a chain of devices. As that chain gets longer and longer, there's a fishtail effect towards the end that will just cause devices to fall out of sync. So then people got smart and said, okay, what if I have one device output a clock, feed that to a distribution amp, and send that to all the other devices? Well, sure, that works. Everyone is one propagation delay behind the leader. But of course, the gold standard is to use an external clock and distribute that to all devices. Every device is one propagation delay away from that leader, which means they are in very tight sync. Now, some people may have experienced an improvement when they brought in a dedicated clock leader. Certainly, the quality of components can have something to do with it, but just as important is an optimal topology. And while we're on the subject of synchronization, let's take a moment to explain the difference between word clock or video clock versus something like SMPTE timecode. If we think about the wall clock analogy, every device has an internal chipset that's like the pendulum of the clock. It tells us to take the next audio sample or the next video frame. But if all I can see is the pendulum of the clock, I couldn't tell you what time it is. All I do is I see the pendulum going back and forth, next sample, next video frame, next video frame. And that's where SMPTE timecode comes in. SMPTE timecode is the face of the clock giving you a position on a timeline. Now, certainly SMPTE timecode and video clock are related. They need to be resolved to each other. If you think about it, if that pendulum shows that 60 seconds have passed, the face of the clock had better show 1 minute passed. If they start drifting from each other, then we have a problem. But clearly, they are measuring different things. Video clock or word clock is just giving you the next tick, whereas SMPTE is giving you a position on a timeline. Now, if this explanation helps, that's great. But if it doesn't, don't worry about it. Dante does not generate SMPTE timecode because it's not a recorder. It's just an audio-video transport getting things to your recorder. So finally, the question comes up, can I send SMPTE timecode as an audio tone across a Dante network? And of course, the answer is yes. SMPTE timecode used to be striped on analog machines and early digital tape machines. That was never a problem. So of course it could go across the Dante network. Now, some people will say, well, I've had problems with digital systems. Usually if you had a problem with SMPTE timecode on a digital machine, it was something that used compressed audio. Dante does not use compressed audio. We won't have a problem with it. All right. With that, let's get back to clocking and let's explain how Dante devices choose a clock leader. As we know, Dante devices will automatically discover each other on the network. From there, we use precision time protocol for sync, and that protocol has a process called the BMCA, Best Master Clock Algorithm. That will automatically choose a clock leader on a multitude of parameters. Let's suppose a device is chasing an external word or video sync. That would certainly be common when integrating with video teams that are still using SDI, for instance. Okay, no problem. The device that's chasing external clock will be elevated in the process. We figure we probably ought to follow it because it isn't going to follow us. Finally, we have a preferred leader option. Now this is where you can designate which devices should be allowed to be the clock leader. So of these three systems, the preferred leader is the highest priority. Whatever you choose will win out. After that, any device chasing external clock will win. Now, because preferred leader beats it out, anytime I have a device chasing external clock, I also set it as a preferred leader. And of course, finally, after that, the best clock algorithm will kick in and choose a leader for us. So let's walk through a couple of scenarios and see how this plays out. We'll start with a number of devices at the bottom and step through each step of the election process as a leader is chosen. You can see I have some devices checked for a preferred leader and some for external sync. So let's go through the process. The first question is whether any devices are chosen as preferred leader. In this step, we can see 3 of them are, so they move on in the election process. The next question is whether any are chasing external sync. Okay, 2 of them are, so they move on in the election process. At the end, we always have the best clock algorithm, which will choose one of the remaining candidates. And a clock leader is chosen. Okay, let's reset. What happens if no devices are chasing external clock? Well, the first step runs as normal. The 3 devices are selected as preferred leader, so they move ahead in the election process. When we ask if anybody's chasing external clock, no one is. Well, if we end up in a situation where all candidates would be eliminated on a particular step, we instead pass all of those to the next level. Finally, we have the best clock algorithm to choose one leader out of the remaining candidates. Now let's do this one more time. Let's suppose nothing is marked for preferred leader or external sync. Basically, this is what happens when everything comes right out of the box. Well, in the first step, No device is set as preferred leader, so all candidates advance. In the second step, again, no device is set to chase external sync. So again, all candidates advance. And finally, the best clock algorithm will choose one leader. Now let's show this in action. In the Clock Status tab in Dante Controller, we can see all of my devices are getting their clocking information from the Dante network. One device has been chosen as the leader, the rest are followers. Let's suppose I wanted to choose the mixer to be my clock leader. No problem, I can check its preferred leader box, and the mixer takes over that role. You'll notice no devices are muting. It should be a seamless process. Now let's change this around. Let's suppose I want to have a Dante AV video device take over the clock leader role. No problem. I check the preferred leader box for that device, and it takes over. Okay, so what happens if I have multiple devices chosen as preferred leader? Well, one of those will be selected as a clock leader. When I remove the video device as a preferred leader, one of the 4 remaining devices at the bottom will take over. Out of those 4, the best clock algorithm will choose for us. All right, so that's a basic demo of preferred leader. Now let's talk about external sync. When you set up a device to chase external sync, you often have to make settings inside the main device, right? Right now, this device knows it's chasing clock from the Dante network, but we can choose to chase the word clock input instead. Now we'll see the mixer mute as it switches to its new clock source. The devices on the network are muting as well because the new clock is not necessarily close to what our previous clock was. Once everything settles, go into Dante Controller and ensure that the Enable Sync to External checkbox is ticked. Also, under the clock source column, you'll note that this device is now receiving clock from an external source. Now typically, if your device has a Dante port built in, choosing an external word clock on the device will automatically update the Dante chipset, which will automatically update in Dante Controller. That checkbox will automatically be ticked for you. However, if a device uses an option card, the option card might not have a control link to its host device. So in that case, going into your mixer or your DSP and telling it to chase external clock, you would still need to go into Dante Controller and check the box. This check mark here isn't just a matter of elevating it in the clocking process. It does tell the chipset internally where to find the clock. Does it find it on the Dante network, or does it look to its host device? Okay, so we know how to make our clock settings. Now let's talk about how accurate the clock is. Back in 2013, Yamaha did a test that measured and demonstrated many of the principles I just explained. They started with 2 consoles following an external clock. They take their word clock outputs and put them up on a scope. Sure enough, the signals lined up perfectly. This is our gold standard, right? Okay, what if we have one console feed a digital stream to the other using AES-3? The second console then clocks from the digital input that's being fed to it. Now let's take the word clock outputs of the console and compare those. Now we see the propagation delay. Okay, what if we have the second console follow the first using CobraNet? Again, we see the propagation delay. All right, what if we have 2 network switches between the consoles instead of 1? We get different amounts of propagation delay on different parts of the network simply because it takes longer for the message to get there. Now the second graph looks like it's closer in time, but you have to realize the system was really offset by more than 1 cycle at this point. Okay, so what if we do this with Dante? We have one console sending clock to the other across the network, and it's spot on. It really looks very much like the graph from the BNC word clock distribution, doesn't it? Okay, what if we have 2 network switches? Spot on again. So how does this happen? Doesn't it also take longer for Dante packets to get across the network? Well, of course it does. So let's explain why this is so. Dante uses precision time protocol. That synchronizes a time and date stamp between devices with sub-microsecond accuracy. That's better than a millionth of a second. All devices will derive the word clock, video clock, or whatever sync mechanism they need from that reference. So we'll have a leader and a follower. It starts just as you would expect, synchronizing time. Now that's just like synchronizing our watches. And as you would imagine, to fight drift, we continually send out follow-up messages. But we don't just set our watches again. Precision Time Protocol remembers timestamps and compares them. If you figure out the difference in time between the two stamps from the clock leader and the two stamps from the clock follower, we can start to figure out if the follower's clock is running fast or slow, and we can start making adjustments to match. See, if all we did was resync every time a stamp came in, we would have jerky movement like this. But because we match speed, the follower's movement can be much smoother like this. This concept totally changed the way synchronization worked across the network. Predecessors to Dante worked just like AES-3, right? They would transmit data, and then when it was received, that was used as a clock pulse. Dante works differently. You'll remember that clocking packets are sent out separately, and by using quality of service, we can elevate those clocking packets to a higher priority queue. That means the clocking packets can move through the network uninhibited, achieving exceptionally low jitter. Now, some of you are probably thinking, well, what happened to propagation delay? Certainly we understand that we could compare multiple timestamps to match our speed quite precisely, but it should still take time to get our packets across the network, right? To address that part of the puzzle, Precision Time Protocol issues delay requests, which calculates the latency of the network. By comparing these stamps, we can figure out how much time it takes for the messages to get across the network, and we can adjust our clock accordingly. Without these follower messages, the followers would always be a bit behind the clock leader. But with the addition of the follow-up messages, we can ensure our clock leaders and followers will reflect the same time with sub-microsecond accuracy. And with that, it's time for a summary. So Dante automatically elects a clock leader. It uses Precision Time Protocol to establish a time and date stamp with such accuracy that each device can derive the clock they need from it. As such, there will only be one clock leader, regardless of how many sample rates or video frame rates exist. The external clock and preferred clock leader settings will elevate devices in the clock leader election, allowing you to influence who wins without sacrificing robustness if devices join or leave the network. And we know that Dante clocking is exceptionally accurate, correcting for internal time variations and propagation delay across the network. Now, if your network is occasionally dropping network packets, that's certainly something to solve, but it's not a reason for total panic. We have seen customers accidentally block the clocking traffic on their network, and their Dante devices remain stable for minutes or possibly even hours after the clocking data was removed. So don't worry, clocking is very stable.